Right now, while you're watching this, there's a hole open in the sun's outer atmosphere, and a stream of charged particles pouring through it is on a direct path toward Earth, expected to arrive within hours. NOAA's Space Weather Prediction Center has already issued a geomagnetic storm watch covering tonight through tomorrow, July 22nd, and the number behind that watch is striking. Solar wind speed is forecast to more than double, climbing from a normal background pace of around 325 kilometers per second to somewhere near 700 kilometers per second in less than a day. If that speed holds, forecasters expect conditions to escalate from a minor G1 level geomagnetic storm tonight into a moderate G2 level storm tomorrow, strong enough to push the northern lights south of the Canadian border into Washington State, Montana, and Michigan, and to light up skies as far from the pole as Edinburgh, Oslo, and the southern tip of New Zealand. And that's not even the most active thing happening on the sun's surface at this moment. A brand new sunspot region, cataloged only 4 days ago, has already become the single most productive flare source anywhere on the visible disk. A second, older region sitting nearby has grown so magnetically tangled that forecasters now consider it the most likely candidate for a major eruption. This combination is why meteorologists and space weather forecasters are calling this the sun's critical week, and it's happening while our star remains deep inside the most active phase of its 11-year cycle. No exaggeration here, just what the forecasts actually show, and what it would mean if the numbers behind them keep climbing. Drop a comment and let me know if you can spot the aurora from where you live tonight. I read every one of them. If you want space weather coverage that actually explains the mechanism behind these events instead of just showing you a pretty photo of green lights, subscribe. It costs nothing, and it helps put this in front of more people before the storm arrives. Let's push for 5,000 likes on this one. Thank you. Now, let's get into it. To understand why this particular week matters, you first need to understand that the sun doesn't threaten Earth in just one way. It threatens us in 3 distinct ways, and forecasters track each one separately because they behave completely differently from one another. The first is a solar flare, a sudden burst of radiation from the sun's surface that reaches Earth in about 8 minutes, which is simply the time it takes light to cross the distance between us. Flares are ranked by strength using letters. A, B, and C-class flares are weak background events with essentially no effect on Earth. M-class flares are moderate and can cause brief radio disruptions on the sunlit side of the planet. X-class flares are the strongest category that exists, powerful enough to cause radio blackouts across entire regions the instant they arrive. The second threat is a coronal mass ejection, a genuinely enormous cloud of magnetized plasma, sometimes weighing billions of tons, that gets hurled outward from the sun and takes 1 to 3 days to reach Earth. Because it travels slower than light, a coronal mass ejection can actually be forecast in advance once it's observed leaving the sun, unlike a flare, which gives almost no warning at all. The third threat, and the one driving this week's alert specifically, is a high-speed stream flowing from a coronal hole, a region where the sun's magnetic field opens directly outward into space instead of looping back down to the surface. This open configuration lets solar wind escape at much higher speed than normal, sometimes reaching 500 to 800 kilometers per second instead of the usual 300 to 400. None of these 3 phenomena is the same event, and this week, Earth happens to be dealing with the influence of all 3 at once, though the coronal hole stream is the one arriving first. The story of this critical week actually begins about 3 weeks before today, on June 30th, when an active sunspot region designated AR4479 unleashed an X1.1 class solar flare, the first strong warning sign that this stretch of the solar cycle was entering a genuinely hyperactive phase. What made that event remarkable wasn't just the flare itself, but what happened in the 24 hours immediately afterward. The same region fired off 10 additional M-class flares in a single day, a pace of eruptions so unusual that space weather physicist Dr. Tamitha Skov began referring to the region on her public forecasts as the machine gun sun. Several of those eruptions also launched coronal mass ejections toward Earth, and because they were released so close together in time, some of them caught up with one another during transit and merged into a single, stronger disturbance by the time they arrived. That merger prompted NOAA to issue a G2 moderate-level geomagnetic storm watch for July 3rd and July 4th. A forecast that, as we're about to see, turned out to badly undersell what actually happened when the storm reached Earth. That storm arrived almost exactly on schedule. And then, in the way space weather sometimes humbles even careful forecasters, it turned out far stronger than the watch had predicted. It escalated into a G3, strong-level geomagnetic storm right on the night of America's Independence Day, producing aurora visible across roughly 30 separate U.S. states, far further south than a G2 watch would normally suggest. That gap between forecast and outcome is worth remembering because it reveals something important about how these storms actually get predicted. The speed and timing of an incoming disturbance can be estimated fairly well once it leaves the sun. But the single most important variable, the north-south orientation of the magnetic field buried inside the incoming plasma, can't be measured until the storm is already almost on top of us, at a monitoring point called L1, roughly 1.5 million kilometers from Earth. That typically gives forecasters only 15 to 60 minutes of final warning before impact. For the 2 weeks following that Independence Day surprise, the sun actually settled down considerably. Forecasters described conditions through the middle of July as quiet, with the Interplanetary Magnetic Field Week and Earth's own magnetic field staying calm, sitting at the lowest levels on the standard geomagnetic activity scale for day after day. But quiet on the sun rarely lasts. On July 17th, a small, unremarkable-looking sunspot appeared near the southeastern edge of the visible solar disk, captured by NASA's Solar Dynamics Observatory before it had even been given an official designation. Within 2 days, before it had even fully rotated into view, that region, now cataloged as AR4491, had already become the single strongest flare producer anywhere on the sun for 2 consecutive days running, an unusually fast escalation for a region that had barely finished forming. At the same time, a separate, older region designated AR4489 developed what solar physicists call a beta-gamma magnetic configuration, a technical way of describing a sunspot group whose magnetic polarities have become so tangled and compressed against each other that the region is considered mechanically primed to release a significant flare, without anyone being able to say exactly when. As of this week, forecasters put the odds of a common C-class flare from these regions at 50% or higher, with a smaller but real chance of another M-class event, while stating that a major X-class eruption isn't expected in the next few days specifically, though that assessment could change within hours if either region continues to grow more complex. And then, arriving on top of both of those active regions, comes the specific event driving today's alert. A large coronal hole stretching across the sun's equator, angled so that its high-speed stream is aimed almost directly at Earth. The mechanism behind this kind of storm is genuinely different from a flare or a coronal mass ejection, and it's worth explaining, because it's exactly why forecasters can give a multi-day heads-up for this one specifically. A coronal hole isn't a hole in the sense of an empty gap. It's a region where the sun's magnetic field lines don't loop back down to the surface the way they do almost everywhere else, but instead open directly outward into space, like an unlatched gate. Through that open gate, solar wind escapes far more freely and at much higher speed than the background solar wind flowing from the rest of the sun. Because coronal holes rotate around with the sun roughly every 27 days, the same one can sweep past Earth's position again and again, which is exactly why this particular pattern was flagged days in advance rather than discovered only when it arrived. Forecasters at NOAA, at the UK Met Office's Space Weather Operations Center, and independent trackers all converged on the same basic forecast this week. Quiet to slightly unsettled conditions through most of July 20th, then a shift late on July 21st as the leading edge of the stream arrives, escalating into a period of active to G1 minor storm conditions through July 22nd, with wind speeds potentially reaching 700 kilometers per second at the peak before gradually easing by July 23rd. The most visible consequence of a storm like this one, and the one most people actually care about, is the aurora. It's worth understanding exactly why a coronal hole storm produces a different kind of light show than a coronal mass ejection does. When charged particles from the sun strike Earth's magnetic field, they get funneled down toward the poles, where they collide with oxygen and nitrogen atoms in the upper atmosphere and cause them to glow. Oxygen typically producing the greens and reds most people associate with the aurora, and nitrogen contributing the blues and purples seen in stronger displays. Under normal, quiet conditions, that glowing ring sits tucked up near the poles, invisible to almost everyone. During a G1 storm like the one forecast for tonight, that ring expands just enough to become visible from the very northern edges of the continental United States and from northern Scotland. And if conditions reach G2 intensity, as some models suggest they might, visibility could push further south still, into cities like Seattle. Still, there are 2 real obstacles working against skywatchers this particular week. First, this storm is being driven by a coronal hole rather than a coronal mass ejection, and coronal hole-driven storms tend to be steadier but weaker than the sudden, sharp spikes a well-aimed CME can produce, meaning the display is more likely to be a modest glow than the kind of dramatic show that made headlines back in early July. Second, this is currently the height of Northern Hemisphere summer, meaning nights are short and never get fully dark at higher latitudes, and a first quarter moon this week is adding extra light pollution on top of that. Both factors make a faint aurora considerably harder to actually see with the naked eye, even where the geomagnetic conditions are technically favorable. But the aurora, however satisfying it is to look at, is really just the visible symptom of something with much larger stakes attached. This is where the phrase critical week starts to earn its meaning rather than just serving as a catchy headline. All three of the mechanisms driving space weather, flares, coronal mass ejections, and high-speed streams can degrade or disrupt technology that modern life quietly depends on. Strong flares cause radio blackouts on the sunlit side of the planet within minutes of arriving, disrupting the high-frequency communications used by aviation and maritime shipping. Geomagnetic storms of any origin can degrade GPS accuracy and timing signals, which matters far beyond a car's navigation screen, since those same GPS timing signals are also used to synchronize financial trading systems, cellular networks, and power grid operations. Satellites in low Earth orbit experience measurably increased atmospheric drag during periods of high solar activity like the one we're currently in, because the extra energy pumped into the upper atmosphere causes it to expand outward, quietly shortening the operational lifespan of thousands of satellites during a solar maximum like this one. And the most consequential risk, though also the rarest, involves the electrical grid itself. When a strong enough geomagnetic storm induces slow, direct current-like currents through long, high-voltage transmission lines, those currents can overheat and permanently damage the large transformers that keep regional power grids running. Equipment that is often custom-built to order, with lead times measured in months or even years. That means a bad enough storm could, in theory, leave a region without power for far longer than an ordinary outage ever would. To understand what a genuinely worst-case version of this looks like, it helps to go back to the one event every space weather forecaster still uses as the benchmark, a solar storm from September 1st and 2nd, 1859, remembered today as the Carrington event, after the British astronomer who documented it. During that storm, the aurora was so bright that people in the northeastern United States reportedly read newspapers by its light alone, and it was visible as far from the poles as the tropics. Telegraph systems across Europe and North America failed outright, and in a detail that still amazes engineers today, some telegraph operators discovered they could disconnect their batteries entirely and continue sending messages using only the electrical current the storm itself had induced directly into their wires, while other equipment sparked and, in a few documented cases, caught fire. In 1859, that was largely a spectacle, since society at the time ran on little more than telegraph wires and steam power. But a joint 2013 risk assessment by Lloyd's of London and the Atmospheric and Environmental Research Group modeled what a storm of that same magnitude would do to the modern North American power grid, and the range they produced is genuinely sobering. That assessment estimated between $0.6 and $2.6 trillion in economic damage, with somewhere between 20 million and 40 million Americans losing power for anywhere from 16 days at the low end to as long as 1 to 2 years at the extreme high end, concentrated along the corridor between Washington and New York, across the Midwest, and along the Gulf Coast. The United States National Academies of Sciences separately produced its own estimate, placing the cost of a similar event near $2 trillion once disrupted telecommunications, banking systems, and GPS infrastructure are factored in alongside the grid itself. We already have a real, smaller-scale preview of what a partial version of this looks like. In March of 1989, a much weaker geomagnetic storm collapsed the entire Hydro-Quebec power grid in about 90 seconds, leaving 6 million people without electricity for roughly 9 hours, while satellites experienced anomalies in Aurora were reported as far south as Texas and Florida during the same event. And we came closer to a full-scale repeat more recently than most people realize. In July of 2012, a coronal mass ejection of genuinely Carrington-class strength crossed directly through the exact orbital position Earth occupies, missing our planet only because Earth itself had rotated to a different point in its orbit roughly 1 week earlier. Statistically, researchers estimate the odds of another Carrington-class storm actually striking Earth in any given decade at somewhere around 10 to 12%. A low enough number that it isn't a daily worry, but high enough that multiple national space agencies now treat it as a real, ongoing planning risk rather than a historical curiosity. All of this is unfolding during a period solar physicists call the solar maximum, the most active phase of the sun's roughly 11-year cycle, officially declared by NASA and NOAA to have begun back in October of 2024. Unlike a single sharp peak, a solar maximum typically stretches across a year or more of consistently elevated activity, with sunspot numbers, flare frequency, and coronal mass ejection frequency all remaining well above the quiet baseline levels seen earlier and later in the cycle, before gradually tapering off as the sun heads toward its next solar minimum later in the decade. That broader context is exactly why this week doesn't exist in isolation. The machine gun sun event in late June, the surprise G3 storm on Independence Day, the rapid emergence of an already hyperactive new sunspot region just 4 days ago, and tonight's coronal hole-driven storm aren't 4 unrelated stories. They're 4 data points inside the same active window, produced by a sun that remains, right now, near the most turbulent stretch of its natural cycle. So what does this actually mean for you tonight and in the days ahead? If you live anywhere near the northern edge of the continental United States, in northern Europe, or at similar latitudes in the southern hemisphere, it's worth stepping outside after dark tonight or tomorrow night, away from city lights, and looking north, since a genuine, if modest, chance of aurora is on the table through July 22nd. If you don't see anything, don't assume the forecast was wrong. Short summer nights and this week's moon are working against visibility, regardless of what the geomagnetic numbers actually do. Beyond the aurora itself, if you work in aviation, GPS-guided agriculture, or anything depending on precise satellite timing, it's worth knowing that NOAA's Space Weather Prediction Center publishes free public forecasts the same way the National Weather Service does for ordinary weather, and checking it during a stretch like this one costs nothing. The bigger picture lesson from this particular week isn't that a Carrington-level catastrophe is imminent. The specific combination of speed, orientation, and direct hit required for that remains rare. The real lesson is that our technological dependence on GPS, satellites, and interconnected power grids has grown enormously since the last truly severe storm struck us in 1859, while our infrastructure's actual hardening against that risk has grown considerably more slowly. That gap is precisely why space weather agencies around the world now treat weeks like this one as worth tracking in real time, rather than waiting to react only once something has already gone wrong. To bring this all together, the sun is entering this stretch of days already primed by a month of unusually high activity. It started with the machine gun sun eruption of 10 M-class flares in a single day, back on June 30th, followed by a geomagnetic storm that outperformed its own forecast on Independence Day, followed by the rapid 4-day emergence of a brand new region that immediately became the sun's most productive flare source, and now capped by a coronal hole stream expected to more than double solar wind speed, and push geomagnetic activity to G1, possibly G2, levels through July 22nd. None of this guarantees a major event. Forecasters are explicit that an X-class flare isn't expected in the immediate days ahead, but it does mean the underlying conditions for one, an active sunspot region with a genuinely tangled magnetic configuration, are sitting on the disk right now during a solar maximum period that NASA and NOAA say is still ongoing. Behind every one of these technical terms sits a real, practical stake. A farmer relying on GPS-guided equipment during harvest season, an airline rerouting a polar flight path around a radio blackout, a grid operator somewhere along the Washington-New York corridor watching a geomagnetically induced current reading tick upward on a control room screen, all of it connected to the same sun that, tonight, might also just give you a faint green glow on your northern horizon if you're willing to step outside and look. We're going to keep tracking this the same way we did today, straight from NOAA's Space Weather Prediction Center, the UK Met Office, and NASA's own solar imaging. Not recycled Aurora photos with no forecast behind them. Subscribe if you want to know the moment either of these active regions actually produces something bigger, because based on how quickly AR4491 went from unremarkable to the sun's top flare producer in under 2 days, it likely won't take long. And leave that comment below. Tell me whether you caught anything in the sky tonight and where you were watching from. Let's go for 5,000 likes on this one. Before you go, it's worth sitting with just how much this 1 week actually captures about where we are in the solar cycle right now. 3 separate mechanisms, a flare-heavy sunspot region barely 4 days old, an older region wound tight enough to be considered primed for eruption, and a coronal hole aimed almost perfectly at Earth have all lined up inside the same 7-day stretch. That kind of overlap doesn't happen constantly, even during an active solar maximum, and it's exactly the kind of pattern that turns a routine forecast update into something worth a dedicated video. What makes this moment genuinely worth your attention isn't fear, it's awareness. None of the forecasts released this week point to an imminent Carrington-scale event. The odds of that kind of direct hit remain low in any given year, even during a solar maximum. What they do point to is a sun that is clearly measurably more active than it has been in years, producing flares, ejections, and high-speed streams at a pace that keeps surprising even the forecasters watching it closely, as we saw when the July 4th storm outran its own G2 watch and became a G3. That unpredictability is the real takeaway. Space weather can be forecast in broad strokes days in advance, but the fine details, the ones that decide whether a storm stays modest or turns into something that reaches 30 states, often aren't knowable until the disturbance is less than an hour from arrival. That's also why the infrastructure conversation matters as much as the Aurora does. Transformers with multi-year lead times, GPS timing signals buried inside financial systems and cellular networks, satellites quietly losing altitude faster than usual. None of these are dramatic on their own, but together they describe a modern world that has built itself on systems the sun can quietly interfere with. The 1989 Quebec blackout and the 2012 near miss aren't ancient history. They're recent enough to be treated as previews rather than curiosities, which is exactly how agencies like NOAA, the UK Met Office, and NASA are treating this week too. So here's where that leaves you. Tonight and tomorrow night, if you're anywhere near the northern tier of the US, northern Europe, or comparable latitudes in the southern hemisphere, stepping outside after dark and looking north costs you nothing and might reward you with a faint green or red glow low on the horizon. If the sky stays dark, that doesn't mean the forecast failed. Between the short summer nights and this week's moon, visibility was always going to be a challenge, regardless of what the geomagnetic numbers actually did overhead. And if you're someone whose work touches GPS, aviation, or satellite timing, this is a good week to have NOAA's public space weather forecast bookmarked, the same way you'd check an ordinary weather app before a storm. We'll keep following AR4491, AR4489, and this coronal hole stream as the week plays out, pulling directly from the same sources we use today rather than secondhand Aurora photos with no data behind them. If that's the kind of coverage you want more of, subscribing helps make sure you see at the moment something changes, and given how fast AR4491 climbed to the top of the flare charts in under 2 days, something probably will. Drop a comment and tell me if you caught the Aurora tonight and where you were watching from. Let's get this one to 5,000 likes. Thanks for watching, and I'll see you in the next one.